let's back up a little bit just to make sure we're on the right page here. We have this problem. Our signaling server is going to be the go-between between these two clients. But at some point, these clients need to send messages directly to each other. But these clients don't necessarily know their own IP address, which is a pretty big problem. If this client's going to be like, hey, send me a message on this IP and port number, what IP port do we even tell the other client? How do we get that set up at all? There's a possibility, which you might wonder, well, the signaling server does know that information. It could handle that. But we do something a little more sophisticated and bring in, I guess not necessarily more sophisticated, but we bring in another server to be able to handle that, which is going to be our stun server, which could be, if you want to build a stun server and a signaling server, they could be the same server. We're not going to do that, but we're just going to build the signaling server. But we're going to use a stun server to solve this problem. So the problem, we're each potentially behind a NAT, a network access translator. And to this device, its IP address is some local IP address, 192.168.05, that is not its public IP address. And it's going to connect to its NAT over some port. Your browser is going to pick some random port value, or probably not random. It's got some algorithm probably to decide what port number to use. And it's going to send a request out to the world, which is first going to hit this NAT. It's going to translate this address into another address. So your NAT, like in your home system, UB is different. We all get our public IP addresses. But at your home internet, your ISP gives you one IP address for your entire household. And you have many devices that are going to connect to the internet using that one IP address. So each individual device is going to connect to the NAT and say, I'm using this port, I'm going to connect to you. And the NAT says, well, I'm going to translate that to some port on your public IP address so everybody can share the same public IP address by all being assigned different ports by the NAT. And then the NAT communicates with the outside world on a single IP address, but a lot of different ports. And then when it receives messages, it checks the port to decide which device that message is for. So it's going to map ports on your public IP address to devices on your network. This is a network address translator. We all have one in our houses. This is how we access the outside world. The downside is our devices don't know this public IP number. There's no real convenient way to find that number. We can't just ask our device, hey, what's your public IP address? Because it does not know. It doesn't know its public IP address. The NAT knows, the outside world knows, but this device does not know. There's no way to just know that from the device. And we could ask the NAT. That would be one possible solution, but sometimes you're behind two NATs. And the first NAT doesn't know anything about the second NAT, doesn't know it even exists. So we need some solution here to be able to address this. The fact that devices don't know their public IP and port that the NAT assigned. And this is the same problem port forwarding solves. I said this last time, but worth repeating, is port forwarding says, hey, NAT, whenever you get a communication over a specific port, send that to my device. Send that to my desktop that's running as a server, because I'm going to broadcast to everybody in the world that they can connect to me on this specific port and this IP address. And when we get messages, that's going to be for this specific device. So that's port forwarding. Say, hey, NAT, that port, forward it to this device. Because this NAT getting a request on this IP address for a specific port doesn't know who that's for unless your device initiated the connection. If you're trying to run a server, you're not initiating the connection. You're just getting random requests, and the NAT doesn't know what to do with those. So that's why we have to have port forwarding if you're running a server. If any of you have been in that situation, that's why. That's what's going on there. Our answer for WebRTC is using a stun server. A stun server is going to solve exactly this problem. It's exactly designed for this. This problem of being behind a NAT and not knowing your public IP address. So what we do is send a message to the stun server, which is going to live in the public internet, and say, hey, stun server, what's my IP and port? Stun server says, this is your IP and port. Now we have that information on the device, and we can send that information to the other client. We're going to use Google's free stun server. It's already in the front-end code for the homework. And when we're testing locally, when both clients are on your same device, we actually technically don't need a stun server. They know their IP addresses. It's both just local hosts, for what it's worth. So they already know this information on both clients when you're testing locally. But once you want this to work outside of one device, because WebRTC is boring on one device, it's only useful for testing, that's when we need the stun server. So we'll use this Google's free stun server, this domain import. So we ask the stun server, hey, what's my IP? And we get our public IP address. The stun server isn't going to know our local IP address, won't even know it exists, but it does know our public IP address, which is the one we're concerned with, because that's how the other client is going to connect to us. So both clients are going to talk to the stun server and say, what's my IP address? And send that IP address as part of a WebRTC candidate or an ICE candidate, which, I did put it, Interactive Connectivity Establishment. I always forget the acronym, so I had to read that one. But an ICE candidate, and send any number of these candidates to the other client. So we have our offer. I always forget what it is. Offer and answer. So we have our offer, WebRTC offer, WebRTC answer, and WebRTC candidate. These are the three types of messages that we need to send between two clients. So whenever we receive any one of these three message types, we're going to forward that to the other client. Again, for our homework, we can assume there are only two WebSocket connections. So we receive a WebRTC candidate, we send it to the other WebSocket connection, and vice versa. WebRTC candidate is going to be the message that's going to test your WebSocket parsing code with buffering. So we test this in Objective 3. How does a router get a unique public IP? It's assigned by the ISP. The ISP, I don't know the exact mechanics, but the ISP says, this is your IP address. I'm going to tell the internet that if they see that IP address, it's going to you. And then the router gets those messages for that IP address. But the ISP handles that. So like your ISP goes to the internet overlords. I forget exactly which entity manages this. And they get a block of IP addresses that they manage, and then it's up to the ISP to make sure that those IP addresses are unique when they hand them out to their customers. Like UB has a block of IP addresses to assign to us on campus, and UB can't go outside of that range. That's UB's range of IPs. I believe they have a few different ranges. But yeah, it's all controlled by some entity. I forget what one it is. One of the web entities. But the WebRTC candidate, this is what's going to challenge, kind of stress test a little bit your WebSocket code. Specifically, that's what I was saying. In task homeworks and objectives, learning objective 3. I should just get consistent naming across all my courses so I don't say the wrong thing. Learning objective 3 of homework 3, when we're doing the buffering, we have you test, we say, change the front end code so it's sending multiple messages basically simultaneously, just back to back. We test that in learning objective 3, but this is where it's going to get put to the test in reality. This is why I even have you bother with that. Because you would see this bug here. These WebRTC candidates, there can be any number of these. A specific client might generate a lot of these WebRTC candidates, or it might only generate one. But it can send multiple WebRTC candidates, and these are happening pretty much back to back with the offer and the answer. All these messages are firing back and forth at a rapid pace. So this is where you're going to have the case where you're buffering in WebSockets, and your last read from the socket might contain the headers of the next WebSocket frame. That situation is almost certainly going to occur when we're going through all the WebRTC negotiation as the signaling server. So that's where your WebSocket code has to be really tight. If your WebSocket code, I kind of went on a little bit of a tangent on the slide, but that's fine. I want to say all this stuff. If your WebSocket code is rock solid, if all your WebSocket code is great, and especially if you have helper methods to parse frames and generate frames, the application objective should be pretty much free. If you have everything working really well up to the application objective, you should start the application objective, be done with it in not too long, and then go, wait, is that all you wanted me to do? And yeah, that's all I wanted you to do. It can be done very quickly. There's not a whole lot there as long as your WebSocket code is working great. If that's finely tuned and everything's debugged, everything's great, WebRTC should be pretty simple and straightforward. If there's a bug in your WebSocket code that you didn't find while you were doing objectives 2 and 3, then WebRTC might just not work. And that's usually an indication that your WebSocket code has a bug. Not necessarily broken. You might still get through the other objectives and get credit for all the learning objectives. But if you're not getting 3s on objectives 2 and 3, you're probably falling apart on the application objective. But once you get your 3s up to the 3 level on objective 2 and 3, the AO should be pretty much free. Anyway, with that, all that said, WebRTC candidate is going to contain a lot of not a lot of information, but a good amount of information. But most importantly, that IP and port for the connection. And there will be candidates for the local connection too, your local IP and local port as well. Even if it is a connection that's going across the internet at large, not just for local testing, but that will be one of the candidates as well. And the clients will negotiate the best connection to use. So if they are on the same network, they'll still talk to the stun and get all their candidate lists, but then they'll test the local connection and say, whoa, looks like we're on the same network. Like we can just connect without using the internet. Let's just connect using the local network. And they'll figure that out. The WebRTC implemented in the browser, the negotiating an ICE connection with these ICE candidates, all of that is designed to be able to find the best connection with all the candidates. So we have all these candidates, and a pair of these candidates will be chosen to be the actual pair of IP and ports that are going to be used for the overall connection, for the final connection, the peer-to-peer connection. Does a client who answers need to use a stun server too? Yes. Yep. Yeah, these are both going in both directions. So you send an offer, an answer, then both clients are going to go to their stun servers, generate all these WebRTC candidates, and these WebRTC candidates are going to be flying back and forth. So each client is going to have a list of the other client's WebRTC candidates, and then they're both going to test those connections and figure out which pair of candidates to use. But yeah, the candidates are sent in both directions. Because both peers need to know the other peer's IP address and port. For sending the messages twice, modifying JavaScript using WebSockets, is there a particular reason for it to not work on Chrome and work on Firefox? In general, it's because you have a bug. I don't know off the top of my head. I'm not aware of one that would cause that specific one. There are some known bugs where I know, like, oh yeah, Firefox does it this way and Chrome does it this way. For that one, no, I'm not. I don't know anything off the top of my head. In general, though, the reason I say it like that, in general, if it's working in one and not the other, you do have a bug, but one of the browsers, it's usually working in Chrome and not Firefox, right? No, this is the other way around. Not Chrome, but Firefox. It's because one of the browsers sees your bug, either sees your bug and says, I know what you meant. Like, browsers are pretty easygoing, especially when rendering HTML. You can have garbage HTML that'll still render fine, and CSS. But browsers will kind of help you out. They're pretty loose with how strict they are. Like, they want to render your page, and they help you out a lot. which can be to your detriment because you don't always see your bugs until you open it in a different browser. I just noticed yesterday in office hours that the image size pushes my text in the header of the page that I gave you, the front end that I gave you. Once you change your profile picture to an image with a different resolution in Firefox, it pushes the text out, or if you have the small elephant, it overlaps with the image. I just found that out yesterday. I shouldn't even admit that, but yeah, I have a bug in there too. Cosmetic only, but Chrome is like, I got you. And Firefox is like, no, you said this. It's for some reason taking the width of the image, even though the image is getting resized, it takes the original width of the image, and that's the size of the containing div. I'll fix it sometime, but it's weird. Chrome doesn't do the same thing. But anyway, it's common for a browser to help you out and then not let you know that you have a bug. And then another browser might be like, I don't know what you're doing. I'm just going to interpret this literally. And then another situation is the browser did not detect your bug. It doesn't even know there's a bug. And it gets into an unknown situation where you have undefined behavior. That undefined behavior just happens to do the thing that you want it to do. But in either case, if it works in one browser and not the other, you do have a bug that really needs to be fixed. But the short answer to this one is no, nothing comes to mind on that particular bug. What could be going wrong there? All right, so we get these ICE candidates, send them back and forth, and this is what one looks like. This is for a local connection. So I have an ICE candidate, and we don't have to, I get this question a lot when it comes to the WebRTC stuff. Your signaling server does not care about the contents of these messages being passed back and forth. I'm just giving this as information in lecture so you understand how the protocol works. For your homework, I'm not requiring you to do any of that. A signaling server does not care about any of that. All it's doing is passing messages back and forth. You get a note from one client, you don't even look at it, you don't even open it, you just pass it to the other client, and that's it. That note, when it's a WebRTC candidate, happens to contain this type of information. We have the connection protocol, UDP in this case. We talked about why we need to use UDP here. It's a live, what word did I use? It's a live streaming, real-time. Real-time was the word I used for this. A real-time live streaming protocol. We really need UDP for that. We have two-way communication. We don't want to have perfect information sent back and forth. We want timely information. Time is more important than accuracy here. UDP is our answer for that one. IP and port, that's the most important piece of information we're getting here. For WebRTC, it's always going to be UDP. So we specify UDP, but it's always going to be UDP. And then the username fragment, this is to identify the connection that we're sending. And some other information that I don't really know. This looks like a timestamp. I generated this last year. But the rest of it, I don't know. I'm sure it's important to someone. IP and port, those are the real big ones. So you get multiple connections or multiple candidates, then the clients will figure out, they'll negotiate which ones to use. But these are the messages being sent back and forth. One of them is going to send an offer, one of them is going to send an answer, both are going to send candidates. Your job is to send each message to the other client. You have exactly 2 WebSocket connections. You can compare connections by reference. So when you get a message over a WebSocket, a TCP connection that's been upgraded to WebSockets, you have a reference to that socket. You have a data structure with references to both connections. You go to your data structure and you say, does this connection equal this connection? If it does, send it to the other one. If it doesn't, send it to this one. So you got some logic that you can use. Comparison by reference is fine for this. Those references will be the same. It's you took that reference and stored it in the data structure. It hasn't changed to a different reference since then. You can do that comparison by reference with just an equal to see if those connections are the same. Or you can do some if you want to check the IP and port and get fancier with it. Knock yourself out. But comparison by reference is fine. And now we can have a peer-to-peer connection. The clients are going to handle everything else. As long as we pass the messages around, clients handle everything else. It's a peer-to-peer connection. The clients should be doing most of the work. And they, in fact, are. I feel like I just said all this stuff. I don't feel like reading the summary. But anybody have questions on this? Okay. After I say you don't have to understand this stuff to do the homework, of course there's not going to be questions. I shouldn't even say that. I should make you implement a stun server. That's what I want to do someday. It'd be a lot more fun. Stun servers, doing the whole protocol is kind of tricky, but the essence of it, of you get a request and you respond with IP and port, that's not tricky at all. You could do that. That's basically in the handout code. I have it print out the client IP and port. You would take that information and respond to the client with that information. It's a little trickier than that, though, in practice, actually implementing the protocol. But I could do like a pseudo stun server. You could handle that pretty easily. Maybe just a what's my IP path. I think that could be done. That would be pretty easy. And fun. I think just to see how you can implement that. Pretty straightforward. I don't know, it's neat. All right, and then servers all step out of the way. The stun server was only there to say this is your public IP and port. The signaling server was only there to pass notes between two people. And once the connection is established, all the servers step out of the way and say, we're done, our job is over, and it's just the two clients connecting to each other over their public IP addresses. There is an option. You can step in to listen to a disconnect message. A client can send your signaling server a request to disconnect that you forward to the other client. We're not doing that, but that is the only reason your signaling server would do anything anymore. Since this connection is just for streaming the audio and video, you're not going to be able to send a disconnect message or any other type of message over that connection. Except the ICE can't, well, I didn't even mention this, but the ICE candidate testing, but the protocol handles that. The ICE protocol handles how to do that. It doesn't handle disconnections. Okay, so you're just going to forward messages. The hardest part, I'd say, the biggest thing students struggle with on this objective is overthinking it. Just don't overthink it. You get one of these three messages. You're checking the message type, by the way. We'll go into the front end, and I'll go through the JavaScript. I don't think we'll get through all of it today, but we'll clean it up on Friday and then do some examples, some general Homework 3 examples. But you get the message. It's a JSON string. It has a message type, which is chat message for everything you're doing in Objective 2, or the rest of the homework, really, except the image uploads. But that message type is always going to be chat message for the chat messages. But if that message type is any one of these three, your task is to take that message verbatim. You're not changing anything. You're not processing anything at all. You're taking that entire message and sending it to the other client. So if you get something from this person, send it here. From over here, you send it there. Without changing the payload at all. You can't just forward the frame itself. You're going to have to call your helper methods, which hopefully exist. Your helper methods that parse the frame, parse the JSON, read the message type, check if it's one of these three. And if it is one of these three, take that entire payload, call your helper method that generates a WebSocket frame out of that payload, and then send that frame to the other client. So as long as those helper methods are there and all your WebSocket stuff is tight, then that should go pretty smooth. And remember, your WebSocket frames that you receive are going to be masked. The ones you send won't be masked. So you can't take all the bytes of the WebSocket frame itself and send them, but the payload will be unchanged. Like the payload length will be exactly the same. If you want to shortcut anything here and you don't have your helper methods and you have a mess of code, you can actually take the bytes of the payload length for these messages and reuse those in the message that you're sending. I don't know if that's going to help any of you. I think that'd be more work than what it's worth. But those bytes won't change because it's going to be the same exact payload length, which is not the case for chat messages. It'll be the same exact payload length. But the masking key will be gone and the payload will be unmasked. That'll be the only change between the frames. Okay, there's a few restrictions with WebRTC. One of them is pretty big. It only works over HTTPS. You can't use a WebRTC over an unsecure connection. It has to be encrypted. If it's not encrypted, the browser says, no effing way, I'm not creating an unencrypted WebRTC connection. There's one exception to this rule, which thankfully it's the one that makes this possible, is unless you're connecting over localhost. So if it's a local connection, it will create that connection, which is fantastic for testing purposes and for our homework purposes. It will work. But if you want to use this same code, you want to go to the hackathon this weekend and build WebRTC, you do need an encrypted connection, or else you're going to have problems. It's going to be errors and nothing's going to work if you're going over an actual network. If you're not connecting two clients that are both on localhost, that's the only way you can get an unencrypted WebRTC connection. So keep that in mind. If you are trying to use this outside of homework 3, it needs to be encrypted, which is homework 4. We're going to talk about encryption next week. So if you do want this, we'll get there. Since I mentioned it, if you do want to do this at the hackathon, you'll get a domain name and then use certbot to get a certificate to get HTTPS, and then do your secure WebRTC connection after that. But it won't work over HTTP, only HTTPS. And sometimes you can't create a peer-to-peer connection. Sometimes there's aggressive firewalls, and sometimes there's dynamic NATs. Might change your port unexpectedly. I guess that's true. But there's something called symmetric NATs, which won't work with this. Symmetric NATs is what I expected to be written on the slide. Symmetric NATs are NATs that will create a connection, or not a connection. They'll assign an IP port combination. Usually there's just one IP address, but they'll assign a port to your machine for communication with one specific other IP address, one specific device, I'll say, one device out there. And then if you want to communicate with anybody else on the internet, any other IP address, it's going to assign a different port. And that completely breaks everything. It seems like a reasonable thing for a NAT to do, one port per person, per communication with somebody outside of the world. The problem is you talk to the stun server. Stun server says, here's the port that you use to connect to me. You say, okay, client, you can use this port to connect to me. Tries to connect to you, and the NAT says, no. That port was just to talk to the stun server. You can't use that port to talk to anyone else. So symmetric NATs, not going to work. Firewalls that are too aggressive, if you're, campus block random ports. It seems like campus might block something at a job. Your IT department might block random things, and it might just block all WebRTC connections. So sometimes we can't create a true peer-to-peer connection, and that's where these turn servers come in. A turn server is that third type of server that we mentioned, the one I say I don't like because it defeats the purpose. But this will do the same thing. It solves the same problem of getting around NATs, but it's way more powerful in the sense that instead of connecting to a stun server to get your public IP and port, and then communicating using that public IP and port, we get around these aggressive NATs and firewalls by connecting to a turn server and then streaming everything through the turn server. So all of our connection that was supposed to be peer-to-peer, it's all going to go through the turn server. The turn server just acts as a go-between that streams all of that audio and video data for the entire connection and does not step out of the picture. Not a true peer-to-peer connection if we need a turn server. But pretty much anything can use WebRTC with a turn server. So no matter what kind of stuff you're behind, as long as you can connect to this turn server, you're going to be able to have a successful connection. So sometimes it's needed, not ideal, but if it's what you have to do and you really want WebRTC functionality, you'd have to have a turn server. And yeah, this defeats the purpose, but like I said last time, if you have infrastructure built around WebRTC and you have a certain subset of your user base that just can't do that because of firewalls and aggressive NATs or anything, maybe you throw a turn server in there and say, look, you can still use our app, but just so you know, it's not peer-to-peer. Maybe, I don't know. But they could still use your app, though. There is a solution for that problem, which is nice to have. But if everybody's using that solution, what's the point of using a peer-to-peer protocol? We're sending messages. That one I read. That one I did. Why does a firewall let data from a turn server come through, but not a peer-to-peer? I don't know. Depends who's maintaining the firewall, whatever firewall rules they're adding. Some IT departments are weird. They'll block random things. I don't have a really good answer for you on this question. But it's up to whoever's writing that firewall and setting the rules. If they're just using an out-of-the-box firewall, I mean, they can block whatever they want. They might just have a list of IP addresses that you can connect to, and everything else is denied. Maybe it's only IP addresses that you connected through using DNS. Actually, that seems reasonable to me. Here, I do have a decent answer for you. It only allows IP addresses that you got through a DNS lookup, and that's not going to exist for peer-to-peer. So the turn server is going to have some DNS, some domain name, and some DNS lookup. And then the firewall will say, that one's fine because you went through DNS. But without going through DNS, just IP address directly, I think it'd be almost reasonable for an IT department in a company to block any of those connections. Maybe reasonable, depending on what kind of company, I guess. I don't know. But that's my example. Again, you can assume exactly 2 WebSocket connections. I think I said that a billion times. Hopefully you all know that by now. All right, any questions on any of that? Let me go to Web App Project. This should be exactly the handout code. I don't know if I modified my JavaScript in that other project. I think I did. So let me go to the handout code just to make sure that it's exactly, we're looking at the same things. So the first thing in the handout code, if you haven't done so already, when you start Objective 2, change this to true. Once you change that variable to true, that's going to switch the site to the Homework 3 code, which is going to have WebSockets and WebRTC stuff. And it's going to have an extra spot in the HTML. So we set this to true. Creating the WebSocket connection. The question I keep getting, we'll get there. Using WebSockets. So sending a WebSocket message. So when in Objective 3, where I say change the code to send multiple messages, take this line right here, where we're sending a message over the WebSocket. This is when a user types something in the chat box and clicks send. This is the code that's ran. And if we're using WebSockets, so if you change that variable we just changed, it's going to use WebSockets. If not, we're going to go back to the AJAX stuff like we did on Homework 2. But for testing multiple messages, that's it. Now when they send, I got this 5 times here. Send a message, make sure it shows up 5 times on all clients. Simple, effective. Now it's going to make sure that your buffering, especially when these messages are large, it's going to make sure your buffering isn't spilling into the next the next WebSocket frame. I almost said stack frame, goodness. The next WebSocket frame, and making sure that you're able to distinguish between all 5 messages without getting them mixed up. Because these are all going to be sent back to back. They're going to be sent fast enough that they're all going to be ready on your TCP socket without being distinguished between reads. Because there's nothing, TCP, if I haven't said this enough, TCP is a streaming protocol. It's just a stream of bytes. And then it's up to us to make some sense out of these bytes. And part of that is distinguishing when one message ends and when the next one starts. And we have a few ways of doing this. Content length for HTTP messages, which we don't really have that issue because we're only using a TCP connection for one HTTP message anyway. And payload length for WebSockets, which we do have to worry about. Payload length is going to tell us when the message ends. First of all, how much we have to buffer to get the whole message, but also when the message ends and when the next one begins. Because we just have a stream of bytes. We have to know where these messages are separated. Payload length is what tells us that. Yeah.
So in terms of like parsing the stream, the TCP stream, like so if you have messages back to back and you're reading in if you're reading in 2048 bytes and like part of that byte is like another message, like would you add the bytes of the other message back onto the stream, or would you like take it out and then like start parsing it again?
Take it out. You can't like shove it back on the TCP stream. What you'll do is set that aside in a variable, process the current stack frame, and then when you go back into your buffering code, grab that as the beginning of your next WebSocket frame, and then start parsing. For homework 3, whenever a new tab is open, it should register the connection as an authenticated user. Yeah, and even if we have an authenticated user on a separate tab of the same browser. Yeah, both connections would be authenticated. Yeah, so if the same, like I open Firefox and I open 2 tabs, I'm logged in on Firefox, it has my auth token. Both tabs' WebSocket connections should be authenticated as that user. Yes. All right, so that's what I mean by the message multiple times. And I would do more than 2. 5 is a good number. But I've seen, in my own testing, I believe, when I just did 2, like I didn't have the buffering issue. Like the first one came, just the way the timing worked, like I didn't have to handle that in my code. But if you have 5, especially if the messages are large, like do 5 and do the messages over 2K each. You're going to ensure that you run into the potential bug. You're going to expose that bug if it exists. But I fear if you only do 2, you might get past this one and then get to WebRTC and have it be completely broken. So I would go to 5 or 10. Geez, I mean, it's not like your fingers are going to get sore doing that. Like, just do 10. It doesn't hurt anything. If you can handle 3, you should be able to handle 100. So there's no issue with this. Could there be a case of nested frames for more than one layer? Nested frames for more than one layer. I'm not quite sure what this means. I'm going to take a guess. There won't be some bytes of one frame in the middle of another frame, if that's what you mean. That won't be the case. The browser should be queuing these up and sending one message at a time. So the bytes won't be intermingled. Should. In this case, they definitely won't be because this is all the same thread, the same, what's the generic term for that? I don't know. The same chunk of concurrency. I don't know what the actual name for that is. But JavaScript's single thread. It's not a thread thing. But everything is concurrent here. True. That should be true. But there should be some queuing system, I would have to assume. All right. Any other questions? I'm going to go into the WebRTC code, and we're going to go through this. I don't think we'll get through all of it, like I said. We'll clean it up on Friday, and then general examples. I'm getting some questions on this, so I think I'll do requesting an arbitrary file off the server with that removing slashes. I always just, in the TAs, we always say just remove the slashes and you'll be good on that. But I'll show you how to actually execute the attack if you want to do your own testing. And, I don't know what other demo I want to do. Oh yeah, and parsing WebSocket frames. I still haven't gone through like a whole WebSocket frame and byte for byte, bit for bit, explain every exact thing that's happening on a live example. So I want to do that as well. And that should fill up all of Friday. I don't think we'll have time to do other things. Unless there are questions, I'd be happy replacing one of those two things with something else. Okay, so let's go through some of this code so we can make room for those examples. First, when we're creating a WebRTC connection, we need to give it some configuration. One thing we're going to need here is a list of URLs for our stun servers. Our list is going to be size 1, but you can have multiple URLs, multiple stun servers. We're going to use Google's free stun server here. Create the RTC connection, the WebRTC connection, using that configuration. So we have a WebRTC object, and I want to use this across multiple methods, so I'm just going to put it up here in the no man's land, I guess. I don't know what to call this. But I'm going to put it up here so I can share it across all these methods. And I want to do this in not necessarily the order that it's in. Oh, I really trimmed this code down. This used to be a lot more code. Start video is where I want to start. So start video, this is where you're clicking start video, what else? Which is just going to fire up your video on the front end. And the video on the front end is actually, it's surprisingly simple to have video on your front end. You create a video element and you give it some data. If you want to play an MP4 on your front page, it's about as easy, it's like a little bit extra, but it's about as easy as putting an image on your front page. The browser does all the work. You just say, hey, here's the path to my MP4 file, just play this. And with streaming, it's not that much different here. This is all I have to play your video. This is it. It's a video tag. I'm going to say I want video and audio. I'm going to call get user media, video and audio. What this is going to do when this method executes, it's going to get the actual media, the media devices, and it's going to notify the user. It's going to say, hey, this tab would like to access your webcam and your microphone. Are you going to let it happen? So when you run this code, as soon as you click Start Video, at least for the first time, it's going to have that pop-up that says, do you want to let this tab access your camera? You should probably click yes if you want to test your homework, but it's up to you. If you trust yourself, I guess. And then this is a promise. If you haven't seen this syntax before, this is a promise. This is going to run concurrently. So once this line executes, the next line of code automatically executes and the method ends. Method's over. And then when this returns, it's going to call this function. This is an anonymous function that takes a stream as a parameter. And this function will be called when this function returns, or this one's technically a method. When this method returns, this function will be called with this parameter, which is going to come from this method call, which is actually going to be the audio video data. So if you haven't seen that syntax, this .then, this means it was a promise, which replaced callbacks. If you don't know what those are, I don't know. I can talk to you some other time when I have more than 4 minutes. But I'm going to get the stream. I'm going to get element by ID, my video. So I'm going to get that video element from the DOM. And I'm going to set the source to that stream. This right here is all you need to actually show video locally. Everything else in this file is WebRTC related. This is it. If you just want to have a page that accesses your webcam and microphone and displays that on the page and echoes your audio, that's it. That's it. And then the HTML that we saw. It's even easier if it's an MP4, but to have streaming from the hardware on the device, that's it. Done. The rest is setting up WebRTC. So let's talk about WebRTC. That's what we're here for. We're going to add this stream, the one that we just set to our source, to our element. We're going to add that to the WebRTC connection as a stream. We're going to call add stream and add our own stream to the connection. And then we're going to set this add on add stream, which is going to take a callback function that's going to be called whenever a new stream is added. So we're going to add another stream, which is going to be the other user stream. Bless you. We're going to add that other user stream to this connection. When that happens, we're going to call this function. And this function is going to do the same thing we did up here, but it's going to get the other video, aptly named other video. It's going to get that other video HTML element and then set its source object to this data stream, just like we did up here. We had a stream directly here, but here data is going to contain a stream, so we got to get the stream element. And that's going to set the other stream to that streaming connection. And even though it's a connection from a far-off land, it's pretty much the same code. We're just going to set the source to that stream. The stream is going to have all the connection information, everything that it needs. And then another function, whenever we receive an ICE candidate, what we're going to do with this ICE candidate, and this is when the browser is generating an ICE candidate. This is the browser either getting its local IP import or going to a stun server and getting its public IP import. And whenever we generate one of those candidates, we're going to send it over the WebSocket and ship it. We're going to put the message type as WebRTC candidate. That's what we're adding, so your server can know that this is a WebRTC candidate message. And then the actual candidate itself is going to go in a candidate key, and that's where all the candidate information that the other client's going to end up reading is going to go. And we have our WebSocket messages. There are 3 different message types we can get: a WebRTC offer, a WebRTC answer, or a WebRTC candidate. When we get an offer, we're going to set some various things on our WebRTC connection. Or actually, we're only going to set 2 things, I guess. We're going to set the remote description